Hello, my chemistry griffins. Mr. Milks here, Atomic Theory Unit 2, video number 3. Today we study the history from Democritus to Bohr. There will be your first Google assignment when we are done with this video. So Democritus, the evolution of the atom. This was way, way back. Look at that picture. He was around before pictures existed. They had to make a statue. That's how old this dude is. Okay, a pretty good statue too. Okay. He pioneered the idea of the smallest unit of matter, and he named it atomos in Greek, which I believe means can no longer be divided. Smallest unit of measure. And he really did this thought experiment where he was thinking about, I believe, cutting an apple. And if I cut that apple in half, all right, now I got half an apple. And if I cut that half in half, then I got a quarter of an apple. And let me just keep cutting that thing and cutting that thing. And eventually, I will get down to the smallest unit of apple I can, where I can't cut it anymore. That is how he got to this idea. And believe it or not, he's not really all that far off. It just took us a while to prove him right. He was way back in 460 years before Christ in Greece. Long, long time ago. Okay? It turned out to have some truth to it. It really did. He just didn't have the scientific ability that we have now to prove it and investigate it. But dude's pretty smart. 1850s, Dalton came along. He's got 5 postulates. See that dude Dalton thinking? He was a thinker. Oh yeah. Number 1, elements are made of atoms that are very small. So he's going to build on Democritus and this. He called them atoms from atomos. He called it atoms. Okay. 2, atoms are of a given element are all identical. It's really good that I almost don't even think about that anymore. Like that is so ingrained in my brain that if it's carbon, it's carbon. Like they're all the same. Every one of them's the same. But we need to say that. Okay? So we all know and it's like base information. Atoms of any given element are identical. Atoms cannot be broken down, created, or destroyed. This evolves into the theory of conservation of mass. I cannot break down or create any matter, but in chemical reactions, I can rearrange these things. Atoms cannot be created or destroyed. Atoms of different elements combined in simple ratios to form compounds. This is another fabulous idea that is also true. Water is H2O. Water is not H3O. Water is not HO. Water is not H2O2. It is specifically H2O. 2 hydrogens, 1 oxygen. Specific ratio. Every water molecule, the same ratio. Okay? Very, very easy idea, but very, very important in the big scheme of things. Number 5, chemical reactions. I can separate atoms, I can rearrange them, but I cannot create them or destroy. We're going to find later on in Unit 5 that we can keep track of them. This is Unit 4. Yeah, Unit 4. Boltzmann-Stoich. We can keep track of them and balance them, these equations. But you got to account for all of them. They're there. I have how many atoms that react. I get those same atoms got to be around when I'm done. Okay, I can't. That's how it works. You have to keep track of them. Then Thomson came along and studied even more. He came up with what's called the plum pudding model because he actually figured out that there is this subatomic particle called an electron. He, in this plum pudding model, here's a picture of it. You'll see it looks like a chocolate chip cookie almost because we call it the plum pudding model. And I don't think there's any of you watching this video right now that knows what plum pudding is at all. But what it is this is gelatin with chunks of fruit in it, I think. I'm guessing. Some people would call this the chocolate chip cookie model because that picture looks a little bit more like a chocolate chip cookie where the electrons stuck in the gooey mass of the cookie itself. The chocolate chips, of course, would be the electrons. And this was his first model. Okay, he discovered this thing called the electron and the fact that it was negative back in just before 1900. And he did this cool experiment that we need to know about called the cathode ray experiment. This is how the old school TVs worked. If you guys remember a TV before flat screens. Do you remember one of those? Probably not. But it went on to this pretty simple theory of magnets that we know. He took some positive magnets. So this guy right here is positive, right? One side's negative, one side's positive. So let's see. Milks. Your smart board, what's going on here? Right, so this guy is, yeah, he's positive, and he's negative. Let me draw that in there so you can see. Positive, negative. And I'm talking about this guy right here, these magnets. Okay, and I get this ray that comes through. Boom, and we know positive and negatives attract, and look, it bends it. And he can pick it up and detect it over here. And look, he was expecting it to go through straight. Well, how's it come? It ended up all the way up there. Well, if he knows what he's shooting through there is an electron, and all of a sudden it goes towards that positive magnet, he says, hey, they must be negatively charged. And that bending gives him a lot of information he got to go on, and he got to further this idea of the atom and what it's made up of. Then Rutherford comes along, and we got some really good information from what's called the gold foil experiment. So this little picture here talks about the gold foil experiment. And he started shooting these alpha particles from here. Alpha particles are these positive particles. He shot them through. This is just to make sure they go in a straight line and condenses them right at this little thin piece of gold foil. And this is a side view of that gold foil right here. So the cross cut of the gold foil is here. Now, this alpha particle comes flying through. We see most of the lines go right through. He was not expecting that at all. He was expecting, it's metal. They would do this. They would do this. And they would do that. And here's another one. Look at these ones. These guys did sideways. So I'm going to redraw a little bit of that while I talk. Those lines I just did, I'm going to draw down here. So here's the bulk of them that went straight through. And notice they didn't hit any of those circles. And then some of them got close enough to the circles that it veered away. And we know something, again, about magnetism, that an alpha particle is positive and two positives will repel. And then ever so slightly, look at this, right here, boom, came right back, hit something. Now these were the least number of data points that he got, the ones that bounced back. And he's got to make sense of all of that data. And what he came up with is some really interesting stuff that is still actually what we believe to be true about the atom to this day. We have not been able to refute any of this stuff. He discovered that they have a positive dense center called the nucleus. That's the piece that reflected some of the sample pieces back at us. Some of those alpha particles came backwards. Okay, he also rationalized that most of the atom is actually empty space. And when we say most of the atoms, look, there's 3 data points here where the alpha particles just went straight through, didn't hit a thing. Now, that's a piece of metal foil. Now, it's foil, so it's pretty thin, but it's still metal, and it's gold. Kind of dense. We would think that nothing would go through it, and things did. And so he had to explain all that stuff. And guess what? We learned a lot about the atom. So here's a little picture of what he kind of came up with. So now I got that positive dense core in the middle. We call that the nucleus. And then these electrons are no longer the plum pudding model. They're on the outside. And then look at all that empty space in between the nucleus and the electrons. Big, big theory that there's all that empty space. We would have never known if all those alpha particles didn't go straight through that foil. Now, Niels Bohr came along, and he got even farther. And he had to explain why, when I gave atoms energy, they would emit light. Because that's what he was working on. He was working on giving them energy, and then they gave off light. We will work on that in lab. We will see what happens. But here's a little picture of what's going on. So here is the energy going in, usually in the form of heat. Okay, and then this electron gets excited, and he comes up here. Now there's a step there, 2 steps in this picture that it went up. That 2 steps is a specific amount of energy. When it's on this side and it falls back down, I give off that exact energy in a wavelength of light that is equal to the energy that went in. Whew, that's saying a lot. So he had to understand and explain all that. And so he showed that electrons are in different orbitals or energy levels. That's where the electrons occur. And you could see that if I were to pick up a green and say give it energy enough that this electron only went up 1 energy level, that would be less energy. And if I gave it a little bit more energy, maybe whoops, that's supposed to be on the first energy level. If I give it a little bit more energy, then I can actually make it go from the first one all the way up to the second one. And these are like steps on a staircase. There's distinct energy levels where this happens and actually gives off light. And it works neat to actually build a spectrum of each element so I can actually identify them. We will do that in a little bit. Okay, so here's another picture of the nucleus and the possible energy levels that go on. Then the wave mechanical model. This is where we are currently at. This is an ongoing model. It is extremely accurate. It is explained with complex mathematics, and I'm talking high-end calculus. This picture to the right shows me three-dimensionally what's going on. Three-dimensional calculus is like Calc 3 is when I figured out how to make an equation for something in a three-dimensional shape. It's, we're not even being, oof, stop. I'm not even going to talk about calculus right now. I'm done talking about calculus. It shows that the electrons do not actually orbit like planets, but they actually randomly move around in these orbitals that have these distinct shapes. And they're described by the math. This is where we are at currently. We haven't made any major movements in it. As a matter of fact, we're still trying to find that last little subatomic particle that has been eluding us. Okay, so here's a real quick picture review of Dalton's model, Thomson's plum pudding model, then Rutherford figured out the electrons were outside. Bohr gave me each energy level to these electrons. Based on how much energy added I put in, I get a specific wavelength out. And then quantum even puts these little shapes now to the orbitals based on S, P, and D, and F. And we gave those orbitals all letters, which is groovy. We won't even have to get into that so much. And this is where we are currently, the wave mechanical model. That one was good. You now have some pages in your packet that you should have just filled out. If you need to go back, by all means, do that. You got your first Google Classroom assignment. Make sure you click Done, please. You watched your video. You did your Google Classroom assignment, which is a few questions. Please click Done. Make my life easy. Come into class. We're going to be ready to do pages 7 and 8 in the Atomic Theory packet. And we done.